Welcome back to Derivability. We're going to continue looking at rigid body rotations in 3 dimensions. Okay, you may want to go back and take a look at my recent video on Euler's equations, just in general. All right, I did a few days ago, but we're gonna do a special case of that right now, and that is if you happen to have a fixed axis of rotation. Okay, so we already know that the sum of the moments about some point, okay, and then previously this point A we said either had to be a fixed point in the body or the centroid of the body. Okay, now since we have a fixed axis of rotation, well, A is going to be some fixed point on the axis. Doesn't much matter what that fixed point is, although the details might work out a little bit differently in each case. The angular momentum components, and again, these are all measured about A, and all the moments and products of inertia are measured about A. It's a little sloppy there, excuse me. Okay, I won't write that for the rest, but that's kind of implied here. Okay, so again, the angular momentum components are not necessarily parallel to or proportional to the angular velocity components for 3-dimensional rigid body rotation. All right, so we have these more complicated components. All right, so what we're going to do here is if we have a fixed axis, then our products of inertia are not necessarily going to be equal to 0. That is the I values that have the mixed subscripts. Those are the products of inertia. Okay, the ones with the identical subscripts on the diagonal of that compound formula there, you might say, are the moments of inertia. Okay, because the axis just going to be is what it is. Okay, and my object over on the left side of the screen, that there's no special symmetry to that object necessarily. Okay, there are special cases in which you would have some symmetry, but this is not necessarily one. It could be, but it isn't necessarily one of them. Okay, so since we have a fixed axis, let's choose that axis to be, say, one of the coordinate axes. Okay, so why not choose it to be the z-axis? Okay, and then at some point in the body here along the z-axis, it doesn't need to be at A, but let's just imagine that we have. I'll just draw it at this bottom point here, although it doesn't need to be. Let's suppose we have x and y axes here as well. Okay. All right. And what we're going to be doing here with this version of Euler's equations, okay, the lowercase omega that exists in this cross product, in general, doesn't have to be the lowercase omega that corresponds to the rotation of this body. It could be some other angular momentum vector. Okay, maybe we could not angular momentum, excuse me, angular velocity vector. Maybe there's some other rotation going on. Okay, but what we do is we just set that equal to omega, little omega, to be able to use this version of Euler's equations. Okay, with the lowercase omega in this formula. Okay, and what that means is that the axes x and y are kind of rotating with the body. Okay, that's what permits us to use this version. Okay, all right. Now, some nice things happen here in terms of simplifying. Okay, because if we have a fixed axis of rotation, the only angular velocity component we have is the z component. Okay, so the x components are all 0, and the y components are all 0. So we have a much simplified version of those angular momentum components. Okay, that means we're also going to have kind of a different or simplified version of the derivatives of those and the cross product. All right, so here we have the components of the angular momentum in the rotating frame. And the idea here is that because our coordinate axes, x and y, and then z, of course, are attached to the body, they rotate with the body, that means that we don't have to worry about time derivatives of the moments or products of inertia. So you can see the dots there indicating time derivatives are only on the z components of omega. Okay, now let's also take a look at the cross product. All right, so here's that cross product, omega cross h, at the end of the equation up top. Okay, again, and there's no reason to include anything in this that we've already decided is 0. All right, so we get a relatively simple looking cross product that only has I and j components down there. Okay, x and y components. All right, now we do have all three x, y, and z components when it comes to the rate of angular momentum change within our rotating frame. Okay, so all we really need to do now is put all of these together to come up with the sum of the moments about our point A, whatever that point happens to be on our axis. Okay, and it's worth pointing out here that again, because we don't necessarily have principal axes due to whatever the axis of rotation happens to be, that means we still have non-zero products of inertia that you see here in the both in the time derivatives and in the cross product. Okay, so let's put those all together. Okay, so putting things all together, we have these moment equations. Okay, and just to kind of sum up here, in the x direction, we have those two components. Okay, in the y direction, we have those two components. And then there's only one contributor in the z direction. Okay. All right. Now, so again, these are Euler's equations. They just happen to be applied to the special case of a fixed axis of rotation. Okay, so there's a few interesting things to point out here. One is that it's probably not all that. First of all, the z component is really not all that surprising. Okay, in fact, somebody taking an intro physics course, like a freshman intro physics course, we could almost have guessed this z component equation. Okay. That's because we have the sum of the moments, or the sum of torques, basically equals I times alpha, okay, alpha being an angular acceleration. So that's what omega z dot is, okay, it's the angular acceleration, okay, and especially if you have a fixed axis of rotation, okay. Now, what is more difficult to guess here is, well, first of all, if you don't know about the products of inertia, then you're not going to guess those other two components for x and y. Okay, and even if you do know about the products of inertia, maybe it's not obvious how they enter in. But omega z dot enters in. Okay, but also notice that even if there is no change in the rate of rotation, we can still have contributors that need a net moment in the about the x or y axes. Okay. So those are often called dynamic bearing moments, okay? Or if these happen to be at some sort of bearing along an axle, sometimes called dynamic bearing reactions, okay? And because they are proportional to omega squared and not simply omega, a power, then they can grow very, very large. at large angular velocities. Okay, so this is what happens when you have something that's rotating, which we say becomes unbalanced. This could be a washing machine drum. This could be tires that are not properly mounted or balanced on an axle of a vehicle. And again, a wagon, maybe not such a big deal, but like a motor vehicle where those wheels are going to be rotating very, very fast. Yeah, kind of a big deal. And if they exceed the strength at the bearings, then you're going to have some trouble. Okay. Now, as far as the moments are concerned, on the left-hand side, okay, these could be couple moments, or they could be kind of like a force multiplied by a lever arm sort of moment. Okay, just all depends on the problem and where you have the reactions all set up. Okay. All right, so that's going to do it this time. Okay, I'm planning another video or two on some rigid body rotations. Hope this has been helpful. Okay, hope you will subscribe to the channel if you like what you've been seeing. Share this with your friends, classmates, and others. And to see you again back on the channel real soon.